13,400,000,000 years, that is how far back the mirrors of a single telescope have learned to see. Not a metaphor, not a rounded figure. A telescope positioned 1,000,000 miles from where you are sitting right now, past the moon, past any human hand that could ever reach it to make a repair, staring so far into the past that the light hitting its gold-coated mirrors left its source before there was a Milky Way to leave from, before there was an Earth, before there was a sun. It gathers photons older than almost everything. And when scientists pointed it at the deepest, oldest, dimmest sliver of sky they could find, expecting confirmation, expecting a tidy universe of faint newborn smudges, structures, mature, massive, glowing structures, sitting in a place in cosmic history where nothing that big was supposed to have had time to exist yet. That is the trouble hiding inside the most successful theory science has ever built about where everything came from. The universe should not have been able to make what James Webb is finding. And that single quiet violation is not alone. It has cousins, a cold, empty scar stretching across the microwave sky. Galaxies. A ripple pattern tilted against all odds toward our own solar system, as if the universe somehow knows where we are standing. Faint concentric rings that one of the most decorated physicists alive says are echoes, memories of a universe that came before this one. They do not reach for the word impossible lightly, and yet it keeps turning up in their papers anyway, footnoted and hedged, because the alternative is stranger still, that the model holding up modern cosmology, built on Einstein's equations and refined for 100 years. Tonight, we travel through that widening crack. We go to the impossible early galaxies that should not have finished growing up. We sit inside the disagreement over how fast the universe is actually expanding. A disagreement two independent methods cannot make go away. We look into a cold, hollow wound in the oldest light in existence, and into the strange, aligned geometry surrounding it that has earned its own ominous nickname. We end at the edge of an idea almost too large to be comfortable, that some of what James Webb is seeing might be an echo of something that existed. If wonder like this keeps you up at night, take a moment to like and subscribe. It helps this kind of quiet, careful storytelling find the people who still want it told slowly. It launched on Christmas morning, the 25th of December, 2021, riding an Ariane 5 rocket out of French Guiana, folded up like something that should not have been able to unfold itself in space, because it did have to unfold itself in space. A sun shield the size of a tennis court, layered 5 sheets thick, each one thinner than a human hair, and an 18-segment gold-plated mirror that had to snap into place with no astronaut nearby to nudge it if a single hinge stuck. NASA engineers called the whole sequence "344 individual failure points." any one of which could have ended the mission silently, permanently, a million miles from help. By July of 2022, the James Webb Space Telescope released its first full-color images, and the phrase that traveled fastest through the scientific community that week was not really about beauty. In the deepest exposure, a single patch of sky, no bigger than a grain of sand, held at arm's length, astronomers began finding galaxies as they looked more than 13 billion years ago, folded into the same frame as galaxies much closer to us like sediment layers in a cliff face. The telescope existed in large part to answer a very specific question, one that had waited for an answer since the 1990 seconds. What did the first galaxies actually look like? Cosmologists had a working answer already. It came from a model called Lambda, CDM, Lambda for the cosmological constant that drives the universe's accelerating expansion. The model predicted small, faint, ragged, chaotic, newborn galaxies in the first few 100 million years after the Big Bang. Scientists expected James Webb to spend its first years quietly filling in that picture with better resolution, sharper detail, more decimal places on numbers that were already roughly known. The satisfying kind, where 100 years of careful reasoning gets to take a bow. That is not entirely what happened. Within months, the survey teams behind two of the telescope's flagship deep field programs, JDS, the jwst Advanced Deep Extragalactic Survey, and CERS, the Cosmic Evolution Early Release Science Survey, began publishing candidate after candidate that did not look ragged or faint at all. They looked evolved. Some looked, for lack of a more careful word, finished. And the deeper the surveys stared, the more of them turned up, until what should have been a rare anomaly started to look uncomfortably like a pattern. It gets stranger. In 2024, a team led by astronomer Stefano Carniani, using JD's data, confirmed the redshift of a galaxy that would come to be nicknamed. Its formal name is JADS-GS-Z 14-0. Its redshift measures roughly 14.32. A number astronomers use as a kind of cosmic timestamp, because the more a galaxy's light has been stretched, redshifted, by the expansion of space during its journey to us, the further back in time we are seeing it. A redshift of 14 corresponds to a universe only around 290 million years old. For comparison, this galaxy was already there, already shining, when the universe itself was, cosmically speaking, still in its infancy. Faint, small protogalaxies at that age were not entirely unexpected. It was how bright it was, and what that brightness implied about its size and stellar mass. JD's GS says 14-0 appeared to be roughly 1,600 light-years across, enormous for its era, and its light suggested a population of stars already numbering in the hundreds of millions of solar masses. That is something with real structure, already through several cycles of star formation, at a point in cosmic history when under the Standard Model. The problem is often described informally among astrophysicists as too much, too soon. Population synthesis models, the calculations that predict how quickly gas collapses into stars, and how quickly those stars accumulate into visible galaxies. Some researchers have proposed that early star formation may simply have been far more efficient than assumed, converting gas to stars at a blistering, almost profligate rate. Others have proposed that dark matter halos in the extremely early universe may have assembled faster than current simulations allow, front-loading galaxy growth in a way the models never anticipated. Both remain live, competing, and slightly uncomfortable patches sewn onto a coat that used to fit better. The astronomers who work on this are quick and genuinely careful to say, this is not evidence the Big Bang didn't happen, and it is not evidence, it is evidence that something about early galaxy formation, the speed, the efficiency, possibly the physics of the earliest stars themselves is not yet understood. AGED's GSZ 14-0 is simply the loudest example. There are now dozens of candidates crowding the same uncomfortable territory. Galaxies at redshifts above 10, above 12, above 13. Each one a fresh data point in a graph that keeps refusing to level off. Here is the part that matters. This is not a single rogue data point that will quietly resolve itself. It is the leading edge of the entire James Webb early universe program, appearing survey after survey, telescope run. Some researchers, only half joking themselves, have started calling the mounting pile of confirmed candidates a galaxy crisis, borrowing the language usually reserved for the Hubble tension, because a handful of anomalies is a curiosity. There is also a quieter, more unsettling wrinkle sitting underneath the headline number, measuring the mass of a galaxy from 13 billion light-years away. It depends on assumptions about how efficiently gas converts into stars, what kinds of stars form first, and how dust distorts the light along the way. If any of those assumptions behave differently in the universe's first few 100 million years, the true masses could shift substantially. Several teams have flagged exactly this concern, cautioning that a few candidate galaxies once described breathlessly as impossible. That caution is honest and worth respecting. It has not, however, made the broader population of overly massive, overly early galaxies. It has only sharpened the question of exactly how impossible each one really is. And once you accept that the earliest galaxies are stranger than predicted, another population hiding in the same data turns out to be stranger still. It gets stranger. They started as a nuisance in the data. Small, faint compact objects with an unusually red color scattered through James Webb's. Astronomers, working the way astronomers often do when a phenomenon needs a working name before it has an official one, began calling them exactly what they looked like. Little red dots. By 2023 and into 2024, teams cataloging the JDs and Sears fields realized these little red dots were showing up far too often to be a fluke. Their light, when broken into a spectrum, kept showing the telltale signature of gas swirling at extreme velocities, except these were not sitting at the centers of large, settled galaxies, the way supermassive black holes usually do in the modern universe. They were showing up alone, or nearly alone, at redshifts above 5, above 7, sometimes higher, meaning the universe had barely finished its first billion years, and something was already growing black holes with masses that current models say should have taken far longer to assemble. Some early estimates put certain little red dots at black hole masses comparable to a healthy fraction of their host galaxy's entire. In our own galactic neighborhood, a central black hole is typically a small fraction of 1% of its galaxy's total stellar mass. Several of these early little red dots appeared to invert that relationship almost entirely, carrying black holes that seemed disproportionately, almost absurdly heavy for their age and their surroundings. Astronomers have proposed several routes to explain them. One idea holds that the earliest black hole seeds may not have formed a slow way from the collapsed remnant of a single dying star, but instead formed directly from the catastrophic collapse of enormous primordial gas clouds, skipping the stellar step. Physicists call these hypothetical starting points direct collapse black holes, and until James Webb, they were a theoretical convenience more than an observed reality. Another explanation proposes that these objects are feeding on gas at rates that violate the theoretical ceiling known as the Eddington limit. A third camp argues the masses themselves may simply be overestimated, the spectra distorted by dense gas and dust in ways current models handle imperfectly. What is confirmed, published, and repeated across independent survey teams is the population itself, hundreds of these little red dots sitting exactly where the standard model says overmassive black holes. Some researchers now suspect they represent an entire missing evolutionary stage in how the universe's very first black holes came to be. And that is where it stops making sense in a slightly different way than the impossible galaxies did. Because if the universe's earliest structures, both its galaxies and its black holes, were forming faster and heavier than physics predicted, that raises an uncomfortable question about the yardstick used to measure the whole timeline in the first place, which is where the next crack in the model runs straight through the instrument astronomers have trusted most: distance itself. It gets stranger. Every expanding universe model rests on a single number. How fast, in kilometers per second, does space stretch apart for every additional megaparsec of distance? Astronomers call it the Hubble constant, named for Edwin Hubble, who first demonstrated in the 1920 seconds that distant galaxies are receding from us. That relationship became the seed of the entire expanding universe picture, the ancestor of the Big Bang theory itself. For decades, refining that one number was considered patient, unglamorous, essential work. There are, broadly, two independent ways to measure it. The first is local. Astronomers use so-called standard candles, Cepheid variable stars, whose brightness pulses in a way directly tied to their true luminosity. Then calculate how fast those galaxies are receding. This is often called the distance ladder method, because each rung of measurement calibrates the next. Adam Rees, a Nobel laureate who shared the 2011 Nobel Prize in Physics for the discovery that the universe's expansion is accelerating, has led much of the modern refinement of this method, and his team's most precise local measurements converge on a Hubble constant. The second method works in the opposite direction entirely. It starts from the cosmic microwave background, the faint afterglow of the Big Bang itself, mapped in extraordinary detail by the European Space Agency's Planck satellite between 2009 by feeding the tiny temperature ripples in that ancient light into the standard cosmological model. Physicists can calculate what the expansion rate must be today, extrapolated forward across the universe's entire history. That method converges on a noticeably different number, close to 67 kilometers per second. Econt per minute gigaparsec, 6 kilometers per second econt per minute gigaparsec. Does not sound like much, but the two methods have each been refined to a precision where the gap between them is now far larger than either measurement's margin of error can explain away. This is the Hubble Tension, and James Webb was in part specifically tasked with resolving it because the telescope's infrared eyes. Astronomers hoped Webb would find that the local nearby measurement had simply been slightly wrong all along, a systematic error hiding in the data, waiting to be found and corrected. Rice and his collaborators published Webb-based confirmations of the local Cepheid distances in 2023 and again in 2024, and the local measurement held steady, confirmed independently by an instrument built specifically to check for the mistake everyone hoped was there. What that means if the tension is real, rather than a lingering calibration issue, is that something in the universe's history between then, the microwave background, 400,000 years after the Big Bang, and now, the local universe, 13 billion years later, is missing from the standard model's bookkeeping. Physicists have proposed exotic possibilities, an early form of dark energy that behaved differently in the universe's infancy, none of these fixes has been confirmed. Each patches the numbers without yet explaining physically why nature would behave that way. Here is the part that matters. It is two independent, mature, heavily cross-checked methods, both now refined, with the same telescope refusing to agree, and a model breaking down on the question of how fast the universe expands, turns out to have a companion crack sitting in an entirely different corner of the sky, frozen into the oldest light that exists. If you could see in microwaves the way you see invisible light, the whole sky would glow with a nearly uniform temperature, a faint afterglow left over from roughly 380,000 years after the Big Bang, when the universe first cooled enough for light to travel freely. Astronomers call this glow the cosmic microwave background, and its temperature varies from patch to patch by only millionths of a degree. Tiny ripples that seeded every galaxy, every star, everything that would ever exist, all mapped in extraordinary detail, first by NASA's WMAP satellite, by the European Space Agency's Planck mission. In 2004, researchers combing through the WMAP data found something that did not belong. A patch of sky, roughly in the constellation Eridanus, unusually and stubbornly cold, colder than statistical expectation. It became known plainly as the CMB cold spot. Planck's later, sharper data confirmed it was real, not an instrumental artifact, and made it, by some measures, the single most significant anomaly in the entire microwave sky. The most sober explanation offered is a supervoid, an almost inconceivably vast region, potentially close to 1 billion light-years across, containing far fewer galaxies than the surrounding cosmos, so empty that light passing through it loses a little extra energy on its way to us, registering some large-scale surveys have found tentative evidence of exactly this kind of galaxy-poor region, roughly along the same line of sight. Other, more recent statistical analyses have argued the supervoid, even if real, may not be large or empty enough on its own to fully account for the cold spot's depth. And so, alongside the supervoid explanation, a bolder proposal has circulated in cosmology for over a decade, discussed seriously enough to appear in peer-reviewed journals, even as it remains deeply controversial. The residual imprint of a collision in the earliest instance of existence between our expanding universe and another one in a picture called eternal inflation. If two such bubble universes brushed against each other or collided outright in that picture, the scar could theoretically imprint itself. No one is claiming this is confirmed. It is one interpretation among several, openly labeled speculative even by the physicists who study it seriously. standing alongside the more conservative supervoid explanation, and the debate between the two remains genuinely unresolved in the published literature. But the fact that a bruise from a universe collision is a live, publishable hypothesis at all, taken up by working cosmologists rather than dismissed outright, tells you something about how strange this single patch of sky has forced scientists to get. And the cold spot, it turns out, is not the only piece of geometry in the microwave background that refuses to look the way an isotropic, directionless universe should look. A truly random universe, expanding uniformly in every direction with no preferred axis, should produce a cosmic microwave background whose largest scale ripples That is what the standard cosmological model requires and largely predicts. That is not quite what WMAP found and Planck later confirmed to even tighter statistical precision. The very largest structures in the microwave sky, the lowest order ripples, called the quadrupole and octupole in the language of the mathematics, sometimes described as the ecliptic plane, and with the direction the solar system itself is moving through space. Cosmologists nicknamed it half in scientific shorthand and half in genuine unease. The unease is specific and well-founded. If the largest scale structure of the entire observable universe happens to line up with the orientation of our small, unremarkable solar system, that is either an extraordinary coincidence or it is telling scientists that something in the way the measurement itself is made is not as isotropic, not as directionless as the foundational assumption of modern cosmology requires it to be. Some researchers have proposed mundane explanations: residual contamination from our own galaxy's dust and radiation that was not fully subtracted from the data, or these explanations would be reassuring if they fully accounted for the alignment, and some analyses argue they do, at least partially. But the anomaly has now persisted across two independent missions, WMAP and Planck, using different instruments, different scan strategies, and different data reduction teams. Some cosmologists now take seriously the more unsettling alternative that the universe may possess some genuine large-scale anisotropy, the assumption that the universe looks the same statistically in every direction and from every vantage point. No one has proven that violation. It remains formally an open anomaly discussed at conferences, argued over in journals, resistant to a clean resolution, but an axis that should not exist, pointed suspiciously close to home, is the kind of anomaly that does not politely disappear with better data. And it is not the only sign that something in the universe appears to be moving or pointing somewhere specific somewhere. In 2008, a team led by astrophysicist Alexander Kashlinsky using data from NASA's WMAP satellite. Known as the kinetic Sunyaev-Zeldovich effect. In principle, if galaxy clusters across the sky are moving in random directions, the way ordinary cosmic structure formation predicts, that distortion should average out to something close to zero across the whole sky. Kashlinsky's team found that hundreds of galaxy clusters spread across a huge portion of the observable sky appeared to share a small but coherent, non-random component of motion, all streaming gently but persistently. They called the effect dark flow, and the name was chosen carefully, deliberately echoing dark matter and dark energy, because like those two, the most conservative explanations proposed that the effect might result from foreground contamination, light from our own galaxy or nearby structures bleeding into the measurement, or from statistical noise inflated by the limited number of very large. Several follow-up analyses using Planck's more precise data did find the original signal weaker than first reported, and some researchers now consider it substantially diminished. That more mundane possibility remains genuinely on the table, and a meaningful portion of the cosmology community leans toward it. But the alternative explanation, the one that made dark flow famous well beyond astrophysics circles, is the one that refuses to fully leave the conversation. Not beyond in the sense of far away within our cosmos, but beyond in the sense of outside the boundary from which light has ever had time to reach us at all, a region shaped in some proposals by the same eternal inflation picture that produces neighboring bubble universes, exerting the faintest gravitational pull across a boundary that no, however powerful, could ever directly see across. Nobody can confirm this. It cannot currently be confirmed by definition, because it describes an influence from outside the limit of what is observable, which is precisely what makes it almost unfalsifiable, and also precisely what is agreed upon across both camps is the raw measurement. Clusters of galaxies in significant numbers moving together coherently in a direction that current models struggle to fully explain from visible causes. Later, surveys have tried to settle the question by simply gathering more clusters further out, in the hope that a larger sample would either firm up the signal The results so far have not delivered a clean verdict either way. Some follow-up work using different cluster catalogs and different X-ray observatories has reported a weaker but still non-zero coherent motion. That kind of stalemate, dragging on for over 15 years now, without either side conceding, is itself unusual in a field that generally prides itself on resolving disputes once better instruments arrive. Dark flow has had better instruments arrive. It has simply refused, so far, to fully confirm or fully vanish. And a universe with unexplained coherent motion at its largest scales turns out to have a companion problem in how clumped together, or how smooth, that same universe has actually become. Cosmologists describe the universe's texture, how tightly matter has clumped together into galaxies, clusters, and the vast cosmic web connecting them, versus how smoothly it remains spread out it is derived by combining two things: the measured clumpiness of matter in the relatively nearby universe, mapped through weak gravitational lensing surveys that track how the light from distant galaxies is subtly bent by the mass in front of it and the overall density. Planck's cosmic microwave background data lets scientists calculate a predicted S8 value. Essentially, if you start from the ripples imprinted 380,000 years after the Big Bang and let the standard model run forward for 13 billion years, exactly how clumpy should the modern universe have become? Large weak lensing surveys, the dark energy survey, the Kilo Degree survey, and the Hyper-Suprime-Cam Subaru survey among them, set out to measure that clumpiness directly in the universe we actually observe today. Instead, several of the leading surveys have consistently found a modern universe slightly but measurably smoother, less clumped than the microwave background prediction says it should be. It is not the yawning divide of the Hubble tension, but it has now appeared across multiple independent survey teams using different telescopes, different statistical techniques, and different patches of sky, converging on the same mild but persistent tension often quoted in the 2 to 3 sigma range in statistics, high enough that cosmologists no longer wave it away as simple noise. But not yet high enough to call it fully proven. Physicists have proposed several possible culprits. Perhaps neutrinos, nearly massless subatomic particles that stream through the universe largely unimpeded, carry slightly more mass than the standard model assumes, gently suppressing structure growth. Perhaps dark energy itself is not perfectly constant after all, subtly evolving over cosmic time in a way that slows down clumping. Later, perhaps, some argue the weak lensing measurements themselves still carry unaccounted for systematic errors, and the tension will simply shrink. What is confirmed, published, and repeated is the discrepancy itself, a smoother universe than predicted, sitting quietly alongside a faster or slower expanding universe than predicted, alongside impossible early galaxies, alongside a cold wound in the microwave sky, alongside a tilted axis. Alongside a stream of galaxies moving somewhere, the model cannot fully account for each one on its own, might be forgiven as a rough edge waiting to be sanded down by better data. Together, they are starting to look like a pattern of a model straining at its seams, in more than one place, all roughly at the same time in scientific history. There is a particular kind of unease among cosmologists about the S8 tension, specifically, separate from the unease over the Hubble tension, a patch that slows down early cosmic expansion enough to ease the Hubble tension tends, in most models, to make the smoothness problem worse rather than better. A patch that suppresses structure growth, enough to explain why the universe looks smoother than predicted, tends in turn. Physicists sometimes describe this as squeezing a balloon. Press the model into shape on one tension, and it tends to bulge out somewhere else. That difficulty, more than either tension alone, is part of why a growing number of researchers suspect the eventual fix, whatever it turns out to be, will have to be something genuinely new, and even the pattern of when the universe's earliest light was supposed to switch on has begun to blur at the edges. It gets stranger. Sometime in the universe's first several hundred million years, the era cosmologists call cosmic dawn. The very first stars and galaxies switched on and began flooding the surrounding hydrogen gas with enough ultraviolet radiation to strip electrons from atoms across vast stretches. Before reionization, the universe was dark and opaque in visible and ultraviolet light, filled with a fog of neutral hydrogen. After it, that fog cleared. Standard models built from Planck's microwave background data, combined with earlier generations of galaxy surveys, generally placed the midpoint of reionization somewhere between roughly 550 million and 1 billion years after the Big Bang, tapering off as the last patches of neutral hydrogen were burned away. It was a comfortable, well-supported timeline, requiring a slow, patient buildup of galaxies bright and numerous enough to do the job. Surveys studying quasar-light passing through the early intergalactic medium, alongside direct observations of galaxies at redshift above 10, began finding signs that significant reionization and significant star formation, bright enough to drive it, was already well underway earlier than the comfortable timeline allowed. The same problem, posed by the impossible early galaxies and the little red dots. If galaxies this massive and this luminous already existed at 290 to 500 million years after the Big Bang, they were almost certainly Some astronomers have proposed that early galaxies were simply far more efficient at leaking ionizing radiation into intergalactic space than modern galaxies are. Others suspect that the little red dots and their overmassive black holes may have contributed meaningfully to the ionizing radiation budget themselves. Neither explanation is settled science yet. Both are actively being tested against fresh James Webb data as it continues arriving. What is confirmed is the trend, not a single fringe measurement. Cosmic dawn, again and again, keeps arriving earlier in the data than the model's comfortable prediction. It is the same shape of problem showing up a third time in the same corner of cosmic history. Early galaxies, too big, too soon. Early black holes, too heavy, too soon. 3 separate lines of evidence, 3 separate research programs, converging on the same uncomfortable window of time. Some cosmologists have started referring to this cluster of related problems informally as the early universe crisis, distinct from the Hubble tension, though the two may ultimately share a common root cause still hiding somewhere in the physics of the first. What makes it feel different from an ordinary observational puzzle is the direction of the error. Almost every past correction to the standard cosmological timeline historically has nudged some early event slightly later than first thought, as better instruments resolved ambiguous. This time, the correction keeps running the other way. Structure keeps arriving earlier, not later, and a model that has spent decades absorbing corrections in one direction is now being asked to absorb several in quick succession. And it is inside that same ancient light, the cosmic microwave background, that has already produced a cold spot and a tilted axis, that the boldest and most unsettling anomaly of all has been proposed, one that does not just strain the standard model, but suggests there may have been something, however faint. It gets stranger. In 2010, physicist Roger Penrose, who would go on to share the 2020 Nobel Prize in Physics for his earlier work proving that black holes are an inevitable consequence of general relativity, working from WMAP data and later Planck data, they reported finding faint concentric circular patterns embedded in the cosmic microwave background. Rings of unusually uniform temperature variance, subtly but statistically distinguishable from the random ripple pattern. Penrose proposed these rings as direct observational evidence for an idea he had been developing. Instead, existence unfolds as an endless sequence of eons, each one a complete universe, expanding, cooling. At that point, Penrose argues, a universe with no matter and no clocks left to measure. Time loses any meaningful distinction. The end of one aeon in his mathematics becomes indistinguishable from the Big Bang of the next. The circular patterns Penrose and Guzadjian reported they proposed are the scars supermassive black holes leave behind at the very end of the aeon, whose faint imprint could theoretically bleed across the transition into our own universe's earliest light, hence the name that stuck to the phenomenon. Echoes in the most literal reading of the hypothesis of a universe that existed before our own. The claim did not go unchallenged. Several independent teams reanalyzed the same WMAP and Planck datasets using different statistical methods and reported that they could not confirm the rings represented anything beyond the level of pattern expected from ordinary statistical noise, given the sheer amount of data being searched. Penrose and his collaborators, in turn, published rebuttals defending their statistical methodology and reporting additional candidate rings in newer data releases. The dispute remains, to this day, unresolved in the peer-reviewed literature, genuinely contested, genuinely still being argued over by credentialed physicists. It has not been dismissed outright by the wider physics community, and that fact alone is worth sitting with. A hypothesis this extraordinary that the microwave sky itself carries fingerprints from a universe that existed before the Big Bang. It continues to be published, cited, tested against new data, and debated at cosmology conferences precisely because Penrose's underlying mathematics for conformal cyclic cosmology is rigorous enough. And Penrose's proposal, as it turns out, is not the only serious model in modern physics, suggesting that our universe might have a partner or a precursor born from the very same event that created us. In 2018, physicists Latham Boyle, Kieran Finn, and Neil Turok, a longtime collaborator of Penrose's at points in his career, though this particular proposal is distinct from conformal cyclic cosmology, published a strikingly different. They proposed that the Big Bang was not the singular beginning of everything, but rather the midpoint of a symmetry, a single event that produced two universes at once, our own expanding forward through time exactly as observed. DEG expanding in the opposite time direction and filled predominantly with antimatter rather than matter. The physics underlying the proposal draws on a deep symmetry principle called CPT symmetry, charge parity, and time, which holds in slightly simplified terms that the laws of physics should look the same if you simultaneously flip a particle's charge, mirror its spatial orientation, and reverse the direction of time. Boyle, Finn, and Turok argued that if you take that symmetry with full seriousness and apply it to the universe as a whole, the simplest, most natural solution is not one universe beginning at the Big Bang, but a matched pair, ours and its time-reversed antimatter twin. Mirrored across the same origin point, the way a reflection mirrors an object across a pane of glass. What earned the proposal genuine, sustained attention in the physics community, rather than dismissal as an elegant curiosity. The model offers a natural candidate for dark matter in the form of a heavy right-handed neutrino arising directly from the same CPT symmetric framework without needing to be added in separately. It is a model that explains two of physics's largest unsolved problems: what came before or alongside the Big Bang, and what dark matter actually is, from the same single mathematically disciplined idea. It remains unconfirmed. The mirror universe in this proposal would lie on the far side of the Big Bang in a time-reversed direction, meaning it is not a place any telescope, however advanced, could ever point toward and photograph directly. Its evidence, if it exists at all, would have to arrive indirectly through particle physics results, through the precise mass. Some physicists find the proposal compelling specifically because of its predictive economy. Others remain unconvinced that a proposal this difficult to test directly deserves to be called a scientific theory in the fullest sense. One detail keeps the proposal from being dismissed as pure speculation. It does not merely assert its mirror universe. It makes a specific checkable prediction about the mass of that right-handed neutrino, a number that upcoming particle physics experiments and cosmological surveys, a theory that predicts nothing testable, can survive on elegance alone, sheltered from disproof indefinitely. A theory Turok and his collaborators chose the second, harder path, and physicists watching the field say that choice, whatever the eventual verdict, two separate, serious, peer-reviewed proposals, then developed independently using different mathematics and different physicists, in some form on the other side of it, and a century-old framework that was never built to accommodate an idea like that is now being asked to hold all of it at once. None of what has come before this moment exists in isolation. Every anomaly walked through so far sits on top of the same foundation, general relativity, published by Einstein in 1915, describing gravity, not as a force, but as the curvature of space and time itself, combined with the cosmological constant, the term Einstein himself, in biggest blunder. Only for it to be rehabilitated decades later as the leading explanation for the universe's accelerating expansion. Bolted onto that mathematical chassis is cold, dark matter, the invisible scaffolding required to make galaxies form the way they visibly have. Together, the whole structure is known simply as lambda CDM, and for the better part of 30 years, it has been called without much argument the standard model of cosmology, the most successful, most rigorously tested, large-scale description of the universe that physics has ever produced. It has earned that reputation. Honestly, lambda CDM correctly predicted the fine structure of the cosmic microwave background. It correctly predicted the relative abundance of hydrogen, helium, and lithium forged in the universe's first few minutes. It correctly predicted the large-scale cosmic web of galaxy clusters and filaments that surveys have since mapped across billions of light-years. This is not a model that has failed. This is a model that, for a century's worth of accumulated confidence, has succeeded almost everywhere scientists have pointed it. Which is precisely what makes this current moment feel different to the physicists living through it individually. Each anomaly walked through tonight has a plausible, the impossible early galaxies might reflect unexpectedly efficient early star formation. The little red dots might represent a black hole growth channel. The Hubble tension might resolve through some new form of early dark energy. The cold spot might be an ordinary supervoid. The axis of evil and dark flow might both shrink under better statistics. The S8 tension might close as lensing surveys mature. Cosmic dawn's early arrival might simply reflect efficient early reionization. Any one of these alone is a rough edge on an otherwise excellent model, the kind of thing that gets smoothed out with the next decade of data, the way plenty of past anomalies quietly have been. What has changed, and what a growing number of cosmologists are now willing to say openly in conference talks and review papers, is the sheer number of these rough edges appearing at once in the same narrow window of scientific history, largely driven by the arrival of a single transformative instrument. It is one thing for a model to have one. It is a different thing entirely for it to be carrying 8 or 9 simultaneously, spread across galaxy formation, black hole growth. Physicists are, for the most part, still betting on patches rather than a full replacement. New physics bolted onto the existing model, evolving dark energy, heavier neutrinos, more efficient early star formation, some as yet undiscovered subtlety in how the first galaxies assembled remains the most probable outcome in the judgment of most working cosmologists surveyed on the question. That would leave Einstein's general relativity intact and lambda CDM standing, only somewhat more complicated than before, the way physics has absorbed patches before, historically, but a smaller, more provocative minority of researchers now argue for something closer to a genuine crack in the foundation, a possibility, still fully unconfirmed, that gravity itself behaves subtly differently at the largest cosmic scales, or that the universe's story genuinely does extend in some form before what has always been called its beginning. No one has proven this. But it is no longer a fringe position too small to be taken seriously in the room, and that alone marks a real shift from where this same debate stood. It is worth pausing here to be precise about what is being said and what is not. This is a theoretical bound, not a prediction. No credible physicist working in this field is claiming the sky is falling, or that tomorrow's headlines will announce the universe has been secretly disproven. What is being discussed carefully, in hedged and heavily caveated language across the published literature, is a genuine question about the limits of a model. With how much of its architecture might need to change if the accumulating anomalies turn out to be signal rather than noise. If lambda CDM is only incomplete, missing a term, missing an early form of dark energy, missing an efficient channel of early star formation nobody had modeled yet, then very little of what you think you know about the universe actually changes. the age roughly 13.8 billion years. The basic history, from an extraordinarily hot, dense beginning through an ongoing, accelerating expansion. All of that would very likely survive close to intact, wearing a slightly revised set of numbers. But if lambda CDM is instead more deeply wrong than incomplete, if the accumulating tensions in expansion rate structure formation early galaxy growth, then the honest answer is that cosmologists do not yet know what would come next. The universe's confidently quoted age, its ultimate fate, whether it expands forever into a cold, dark future or eventually contracts, currently rests on assumptions about dark energy's behavior that some of tonight's anomalies even the long-settled assumption that there is only one universe, expanding once from a single beginning, is the very foundation that Penrose's echoing black holes and Turok's mirror cosmos are both independently proposing to revise. Scientists who study this are not predicting collapse. They are doing something quieter and, in its own way, more admirable, acknowledging out loud, in front of their peers, that a model can be the most successful framework. That kind of honesty is rare in any human endeavor. It is the discipline working exactly as it should, not defending the model, because abandoning it would be uncomfortable, but following the anomalies. For most of the last century, it was possible to believe that the outline of the universe had essentially been settled, that a beginning, an age, a rate of expansion. James Webb was built, in large part, to add those decimal points, sharper images, tighter numbers, a firmer. Instead, the telescope keeps sending back something closer to postcards from a cosmos that does not quite match the map humanity had already drawn of it. Galaxies too. An expansion rate that will not agree with itself, no matter which honest method measures it. A cold wound in the oldest light in existence, and a strange aligned geometry surrounding it that should not be aligned with anything at all. Rings that one Nobel laureate reads as an echo from before the beginning, and a mirror cosmos proposed independently, running backward through time on the other side of the same event that made us. It may only mean the story is larger and stranger than the version that fit comfortably in 100 years of equations, the way every previous generation's confident map of the universe eventually to an accelerating one nobody expected in the 1,990 seconds. Each expansion of the map felt, at the time, like a crisis. What is different now is the pace of it. A single telescope, in barely 3 years of operation, surfacing more open questions about the universe's basic structure than the previous 3 decades combined, and continuing to point at fresh patches of ancient sky every week, with an instrument still early in its planned 20-year mission. Whatever else it finds, it seems unlikely to spend the rest of that mission quietly confirming what was already believed. Somewhere, out past the orbit of the Moon, an 18-segment mirror keeps gathering light older than almost everything and keeps handing that light back to us, slightly wrong for the picture we already had.